So I'm going to talk about CCS and the last 20%. And I guess I'll start by saying I think that CCS is really a controversial technology. And when a bunch of us started working on this, I didn't think we really thought it was. I think we thought this is very helpful. It's a very constructive addition to the energy system because we can begin to quickly decarbonize the existing sources of emissions and so forth. But in reality, I think that this has become sort of a lightning rod for polarization of the communities that are in one way or another stakeholders in this. So I'll kind of get back to that theme, and much of my thinking today is really trying to find a way to overcome that controversy to make it so that this is a welcome addition to not only helping with the first 80%, but also the last 20%. So where are we today? There are 15 large-scale plants. And what's been really kind of cool is that this has been creeping up rather quietly. So there was the first wave of CCS projects that came along in the early 2000s, late 1990s. And then there was a very big hiatus, during which time I think people grew very impatient. But anyway, now there are 15 large-scale projects, and it's quite remarkable that we have about 30 million tons of CO2 that are being sequestered every year intentionally, that were designed to capture CO2 that would be either used or put underground. And most of it is being put underground in oil reservoirs, but a significant fraction also in saline aquifers. So there's another 15 projects on the books. Now, whether those 15 projects really materialize or not, we'll see. You know, that's been a sort of a history. We've seen that projects come along, they get on the books, and then just disappear. The most famous project of all is the Sleipner project. It began in 1996. The Norwegians, beginning with the early 1990s, they had imposed a carbon tax offshore of $50 a ton of CO2 on their offshore operations. And so they were designing a project that would have about 1 million tons a year of emissions. And this was going to cost them a lot. It was going to cost them $50 million. So they said, well, what do we do? And they decided that they could, they had to separate the CO2 anyway, because they couldn't sell the gas with the CO2 in it, and that they would pump it underground into an offshore aquifer that it would be retained in. And that they would do lots of monitoring, that they would make this an open project and share the results. So that's been going on since 1996, about 20 million tons sequestered, lots of monitoring data, very, very successful project. Now, one can say that was probably the best place to do it because it was offshore and the formations were very good, but nevertheless it was done. So since that time, really beginning around the 2000s, governments around the world have been really interested in this technology. And while they haven't invested anywhere near as much as has been invested in renewables, it has been significant, and a tremendous amount has been learned. If we look at the science of CO2 storage, back in the early days, whereas we could write down the basic physics, we sort of knew what the right equations were, we had no idea really what the parameters were that you would put in those equations, and whether what we knew from soil science and oil and gas and contaminant transport, whether that would translate to CO2 storage. And by and large it has. I mean, there are new things we've learned about the basic fluid flow in porous media, but anyway, so now we have a pretty good understanding and a strong foundation. And the second thing that's been done that's been hugely important is the development of monitoring techniques. So when we put CO2 underground, there's a whole suite of technologies that can track where it's going in the subsurface. And then in addition to that, we can track CO2 leakage on the surface. There are methods developed to do that. So the idea that this is out of sight, out of mind, or sweeping it under the rug, as I remember one of the early New York Times headlines was sweeping it under the rug. It's not that. And then capture technologies, again, they're fairly mature insofar as they've been used a long time for gas cleanup. But they weren't optimized for these problems. So there have been significant advances in the traditional technologies, the amine technologies, and there are many, many scientists working on a whole new classes of technologies that could lower the cost and lower the energy penalty. But the reality is they're still expensive, and you know, the cheapest separations come from things like ethanol plants, where you basically have to dry the CO2. You can sort of do all that and compress it and put it underground for about $20 a ton, and the more complex projects can be over $150 a ton, and even more, especially for these early scale projects. So that's kind of where we are today. So basically, does everyone know about the basic technology of CCS? Or do you want me to, the idea that you capture it from a smokestack, that you separate it, you compress it, and you pump it underground into a structure that is basically a natural structure that can contain the CO2 by the presence of what we call a seal. A seal, it provides a physical barrier to CO2 being able to migrate upwards and then eventually escape in the surface. The physics of how these seals perform is very, very, very straightforward. You basically, the interfacial tension between the fluids and the subsurface prevent the CO2 from entering into the very, very tiny pore spaces of these seals. So that's basically, and that's the reason that we are quite confident you can store CO2 underground is because there's oil stored underground and there's natural gas stored underground for millions of years. So the mere presence of oil and gas reservoirs attests to the sort of soundness of the basic idea that this could be done. Now there are lots of practical details and engineering details how we do it, but nevertheless it's quite straightforward. So if we look at what are the impediments to CO2 storage, number one, cost of capture. I like to think about how does it change the cost of electricity, and so it will increase the cost of electricity generation anywhere from 50 to 100%. So that's significant. So if you're getting gas at 5 cents, it's going to cost anywhere from 7.5 cents to 10 cents a kilowatt hour, as an example. Similarly with coal. So in a world with no carbon price, of course it's too expensive, and we simply aren't going to do it. The second is that there's a concern and a reasonable concern about the security and environmental impacts of CO2 storage, and that's something that we need to continue to work on improving public confidence, because what I find is that when you speak to the public, by and large, the idea that we have layers of rocks underneath the surface of the earth, and that everything is filled with water, and that there's structures that could contain buoyant gases in little teeny tiny pore spaces, all of that is very alien. And so there's a lot of work on sort of basic geology that we're trying to teach, along with the idea of this sort of new approach. So what about global capacity? I would say that these numbers are very, very uncertain. There have been many studies to look at global capacity. Oops, am I at 1 minute? 5 minutes, okay. So many national and international efforts to look at capacity. I think the bottom line is we don't know. I think that a reasonable global estimate is anywhere from about 2,000 to 20,000 gigatons. Yeah, so that's a lot. Of course, it's not available everywhere. There are notable places like Japan where it's completely lacking. China, there are studies which say that it's significant. The storage capacity in China is significant. We've tried to work very closely with the Chinese and found it very difficult to get any data. Data is a state secret, as far as I can tell, but it's not clear which state. It's very, very closely held. So I don't know about China. India is in a more difficult situation. The rocks there aren't really amenable to that. So India, I'm less optimistic on. Okay, so what are the benefits? Obviously, if implemented, a rapid reduction in about 85% of the emissions from an individual facility to which you apply this to, and that's looked at on a full life cycle basis. So what are the risks? I personally believe people's focus of the risk is misplaced. I think many people are worried it will leak back to the atmosphere at appreciable rates, which would negate the effectiveness of this technique. I really think that it's almost impossible to conceive of scenarios where a significant fraction leaks back. My biggest concern is local groundwater environmental impacts, which should be avoided if you select the site project properly and operate it with best practices. However, as one looks around the world, the regulatory systems for oversight of these projects is nowhere as near as mature as, for example, the United States or Europe. So that's the thing that I worry about most, and I would think about designing these projects to be very careful that that won't happen. You know, if CO2 gets into the groundwater, is it a tragedy, a catastrophe? Some joke, oh, you're just making Perrier water. But the reality is that CO2 might carry residual hydrocarbons, which of course would be quite damaging. And by even moderately changing the acidity of the brines, you could release heavy metals and other things. So it's not to be taken casually. Let me see. What do I want to do? Okay. So a little bit, since I've got probably 1 minute, is this an undervalued or overhyped? So I'll say, when I started working on this in the 1990s, I thought this was the last 20% technology. I imagined that everything else would be done first, and that I was working on something that could be, make a helpful contribution decades into the future. That all changed in 2000 when the IPCC was asked to do a special report on carbon dioxide capture and storage. Its visibility rose very, very quickly. There were extremely high expectations that I think were way overly optimistic in terms of how quickly this could be deployed. We then came, I think, what was the perfect storm for CCS. It was the combination of the Great Recession. There was simply no money. Cap and trade failed to pass in our Congress. And the negotiations in Copenhagen resulted in disappointing outcomes and sort of their lack of ambition. And those three things together, everyone gave a big sigh and setback. And we had even at the very end gotten the coal companies and the electric utilities interested, but with this sort of perfect storm, we really saw a retrenchment. And I think we're starting to see ourselves build our way out of it. But anyway, so that's where we are.